Welcome back to Introduction to Statistics. Let's talk some more about hypothesis testing for population means. In the previous video, I showed you how to use the classical approach to do hypothesis testing of a population mean. Now we're going to learn the p-value approach. Before we do so, remember, just because something is possible does not make it wise or correct. You can apply these approaches of confidence intervals and hypothesis testing to any sample, but it may not be the correct thing to do because you have to meet these conditions in order to use those techniques. The last one, that the sampled values are independent from each other. Independence has many different meanings. In our context, we are looking for this. The sample should be less than or equal to 5% of your population size. Okay, and I'm going to start with a more abstract approach to the p-value rather than giving you a word problem. Let's just go ahead and set up hypotheses. A null hypothesis that the mean of the population I'm studying equals 165, and the alternative hypothesis, H1, that the population mean is greater than 165. But just in case you're one of those people who really needs something concrete to think about, let's consider that 165 is the number of babies a tribble can have in a week. And the alternative hypothesis is that they can have more than 165 babies in a week. Some of you will understand what a tribble is, some will not. Let's just go back to the abstract. Mu equals 165, or mu is greater than 165. I will also let you know that I gathered a sample of 30 individuals. I found that the sample mean was 172, and the sample standard deviation was 12. Now that you're a little bit familiar with hypothesis testing, I want to emphasize that the values for alpha and beta are closely related. Remember that alpha stands for the probability of making a type 1 error, which could also be called the probability of a false alarm, saying, yes, there is a change in the population mean when there really isn't. And beta equals the probability of making a type 2 error, which is the probability of missing a change in the value of the population mean. So alpha and beta are closely related. If alpha increases, beta decreases. As alpha decreases, beta increases. So let's say, for the sake of argument, we don't care as much if we make an error and say mu is greater than 165 as we do if we miss it. If we say, oh no, it's not greater than 165, but it really is, that a miss has more catastrophic consequences. So we're going to set alpha higher. We're going to set it at 0.10, or 10%. There's a 10% probability that we will make a type 1 error. So we don't want to make a type 2 error. So now let's compute our test value. That will be the sample mean minus the population mean that we are aware of, divided by the standard error of the mean. So this will be 172 minus 165 divided by 12 over the square root of 30, and that equals 3.20. Now our degrees of freedom equals 29 because it's one less than the number in our sample. This is where our approach changes. We still need the degrees of freedom, and we still need the test value. But now we're going to take those two things to our t-table. So now we're going to look for the p-value using this t-distribution. Okay, the p-value is the area under this t-distribution, with the degrees of freedom equals 29 and t sub 0, our test value, equals 3.20. P-value, okay, remember the area under a curve is a probability. That's where we're getting our p. Actually, looking for values close to that 3.20 on a specific line here. The line we're looking for is degrees of freedom 29. So we're going straight across that row. And 3.20, where would that be? It would be right in between here. Okay? Between 3.038 and 3.396, if you can't quite see that, as small as it is. So our test value, 3.20, would show up right between those two columns. Well, what is in those two columns? Let's move to the top here and find out. The top of the two columns that we were following up, we have 0.0025 and we have 0.001. And remember, those are areas. And looking at this, you can see that the one on the left is larger than the one on the right. Okay? And remember, our p-value wasn't in either of those columns. Our p-value was in between the two of them. But let's put that in the order in which we usually order our numbers, with the smaller one first. And, we have a p-value somewhere between those two values. Okay, but surprise, we're going to bring in another value we've already talked about, and that is our alpha. We set our alpha at 0.10, which is much bigger than either of those. Look at where the p-value is falling in the chain. It is much less than A. It is much less likely to occur than A is. So we reject the null hypothesis. If the p-value is less than alpha, we reject the null hypothesis. We don't know exactly what the p-value is using this chart, but we know it's less than 0.0025, and we know that that is less than our alpha value of 0.10. Therefore, the p-value has to be less than alpha, and we reject the null hypothesis. So basically, this is saying that it is highly unlikely that our sample would have had a mean of 172 if the mean of the population was not greater than 165. There is only the tiniest of probabilities that we could have gotten that mean for our sample if the mean of the population equaled 165. We can say that there is sufficient evidence at the alpha equals 0.10 level of significance that the mean of the population is greater than 165. P-values are a very popular way of running a hypothesis test. You'll often see p-values quoted in statistics and in various medical studies and all sorts of things. But the reason it's so popular now, I think, and has kind of replaced the classical approach, is computers do that for you. Computers will give you an exact p-value. Let's clear the board. Let's talk about fun-sized Snickers bars. Now, this is actually an example from your book, from the discussion. Did you notice? This example was actually developed by Michael Carlisle, a student at Joliet Junior College. So the example involves a quality control engineer that wants to make sure that the Snickers company producing fun-sized Snicker bars of the size that they want to be. In other words, that the mean weight is 20.1 grams. So this quality control engineer grabs a random sample of 11. Now, manufacturers can get into a lot of trouble if their products do not weigh what they say they should on the package. Weigh less than advertised, they're opening themselves up to problems with regulators, problems with public perception, and I don't know if anybody would sue over candy, but it's possible. On the other hand, producing bars that are bigger than they plan to interferes with their budgeting and their profits. On the other hand, shutting down the plant to recalibrate the machine is difficult and expensive, so you don't want to have a false alarm. All these things have to be considered when designing this hypothesis test. So if the mean weight of these Snickers bars is lower than or greater than 20.1 grams, they have a problem. And because it's so expensive to stop and recalibrate, I want the chance of that happening, the chance of a false alarm happening to be very, very small. So this engineer in the example has decided that alpha, the level of significance, will be 0.01. Since the engineer is using such a small sample, he or she would have to run a normal probability plot and a box plot looking for outliers or a skewed distribution. We will assume that the distribution was normal with no outliers. The mean of the sample was 20.301 grams, and the standard deviation of the sample was 0.64 grams. So now we need to calculate a test value. Okay, and that is always the mean of the sample minus the population mean, or the target in this case, divided by the standard error of the mean. So we have a calculation to perform, and that calculation gives us 1.042 for our test value. Actually need one more number, and that is the degrees of freedom. Subtract 1 from 11, you get 10 degrees of freedom. Actually, I've made a very basic assumption here and have not written it down. And that assumption is that the null hypothesis is the mean of this population of Snickers bars, fun-sized, has a weight of 20.1 grams. And the alternative hypothesis is that the mean does not equal 20.1 grams. That's assumed, but it needs to be stated. Okay, so let's move this over here out of the way a little bit, but that's what we're testing. Do these fun-sized Snickers bars have a mean weight of 20.1 grams, or do they not? This is a two-tailed test. Our t-table deals with things to the right. We're going to be looking at what exists to the right of the value 1.042. But it's two-tailed, so we're actually going to also be interested in the area there that is less than 1.042. Let's bring in a t-table. We're going to be looking for degrees of freedom, and we're looking at degrees of freedom equals 10. So we're going to be looking all the way across here, but we are also looking for the value 1.042. It's not on here. What is it between, though? 1.042. Let's make this a little bit bigger so I can even write that in there. Really bigger. 1.042. So we're going to look now up those columns. Along the top here we have possible p-values. Our value was in between those two. So let's pull this chart down. Okay. So let's compare our values. All right, 0.20 is going to be greater than our p-value, which in turn is greater than 0.15, the head of the other column. I don't know if this helps you or not, but it always helps me to put these in order from smallest to largest. But actually we're not done with this analysis yet, because we're not just talking about the area to the right of our t-value. We need that same area in the other tail. This is a two-tailed test. So we're actually going to have to multiply those by 2. So on the left we now have 0.30 is less than our p-value, which is less than 0.40. Now remember, those are probabilities, and our p-value is expressing a probability. So this is a probability that is somewhere between 30% and 40%. In other words, if the machine were not messed up, there would be a 30% to 40% chance that we could get a sample just like the sample that we're working with. That doesn't sound like there's a problem, especially if we remember that our level of significance was 0.01, it was a 1%. So unless we got some mean weight from our sample that was so unlikely that it could only have occurred less than 1% of the time, if things were completely random, then we're going to say there is not sufficient evidence to reject the null hypothesis. We would say there is not sufficient evidence at the alpha equals 0.01 level of significance to suggest that the mean weight of a fun-sized Snickers bar does not equal 20.1 grams. I think that's enough for now. We will continue our discussion during our Collaborate session. See you then.